This morning I made a snack for myself, matcha yogurt and with peanut butter on the top. And as you can see, here is a coffee that I prepared for tomorrow. When I leave this on their own, the snack will melt and the coffee will cool down. And this made me think, why do physical process move in one direction and not the other one? In other words, why do physical process proceed in one direction and why doesn't the reverse ever occur? For example, why does ice melt? Why does cream spread in coffee? Why does air escape from a punch tire? It feels as if everything is evolving toward another form and as if everything is drifting away from order. Does this idea have a name? And the answer is yes. It is entropy. What is entropy? Entropy is often described as a measure of disorder, and this image is convenient but unfortunately misleading, because to understand entropy through this lens, we must first define what disorder really means. So, what is disorder? What does it mean for disorder to increase? In thermodynamics, entropy is actually a measure of the number of microstates a system can occupy. The more microstates available, the higher the entropy. So disorder is really just a rough, everyday way of describing probabilistic spread. For example, which is more disordered? A piece of ice that has been frozen for 24 hours and shattered, or a glass of water, there is no water inside, bottle that I bought from Jungfrau in Switzerland, or a glass of water at room temperature. And most people would say the ice has lower entropy because its molecules are arranged more rigidly and live in fewer possible configurations. Water, on the other hand, can exist in many more microstates and thus has higher entropy. This is surprising and it shows what we need a better way to think about entropy. Explaining entropy through probability is far more powerful and accurate. For example, imagine two small solids, each consisting of 6 atomic bonds. Solid number 1, solid number 2. In this model, the energy of each solid is stored in these bonds, which is 6. You can think of the bonds as tiny containers that hold indivisible units of energy called quanta, and the more energy a solid has, the hotter it is. And this is one of the fundamental assumptions of statistical mechanics. There are many ways for the total energy to be distributed between the two solids while keeping the total energy fixed, and each distribution corresponds to a microstate. For example, when solid A has 6 quanta and solid B has 2 quanta, and there are 9,702 microstates. Of course, 8 quanta can be distributed in many other ways, all in A or all in B or half in each, like 4 and 4. But what's important here is every microstate is equally likely. This is the fundamental assumption of statistical physics, which is the equal probability assumption. Therefore, some energy distribution are more likely simply because they can be realized by a great number of microstates. And entropy is thus a direct measure of the probability of a given energy distribution, and the more evenly the energy spread between the two solids, the greater the number of microstates. So the configuration in which energy is maximally spread, the maximum entropy state, which is the maximum entropy state, is also the most probable. And low entropy, which means energy concentrated in fewer places, and the high entropy, which means energy spread out, represented by many more possible configurations. To explain spontaneous process like hot objects cooling, we need to look at the system where energy moves, because in reality, energy never sits still. So, what does energy do? It continuously hops between neighboring bonds. This is known as microscopic energy exchange or thermal jiggling. As energy shifts from bond to bond, the energy configuration of the system constantly changes. Because the number of microstates associated with widely spread energy is far greater, energy naturally tends to spread out. And in our model, the probability of ending up in the maximally spread configuration is 21%, and returning to the initial state is 13%. And solid I actually gain energy is 8%. And what does this show? That high entropy energy spread configuration are simply far more numerous and therefore far more likely. If you put a hot object next to the cold one warms and the hot one cools. But in microscopic model, there is even an 8% chance that the hot object could get hotter. So why this never happen in real life? Because it all comes down to the system size. And our model is only used 6 pounds. In reality, object contains millions or billions of times more. If we scale up our model to 6,000 bonds and 8,000 bonds energy quanta, the probability of a solid A spontaneously gaining energy becomes an astronomically tiny number, effectively like a zero. So everyday objects contain vastly more particles than this. That's why processes like a hot object spontaneously becoming hotter are statistically impossible in practice. Ice melting, cream diffusing into coffee, and air leaking from a tire are all higher entropy states because they correspond to a far greater number of microstates. There is no mysterious force pushing systems toward higher entropy. High entropy states are simply overwhelmingly more probable. And this is why entropy is called the arrow of time. Entropy is not just a measure of energy dispersal. It dictates the direction in which physical processes unfold. Most fundamental laws of physics are time symmetric. The motion of particles, the mathematics of collision, and the laws of forces still make sense if you are reverse time. And yet in real life, process never run backwards, hopefully. And ice never resembles itself, and cream never unmix from coffee, and cold object never draws energy from a hot one and heats itself further. And the reason is entropy. By the way, this is a Turkish tea. It's very delicious. So the reason is entropy. High entropy states are unimaginably more likely than low entropy ones. Thus, physical process almost inevitably move toward higher entropy, and the early universe began in a state of low entropy. As time passes, entropy increases. For physicists, the past is the state of lower entropy and the future is the state of higher entropy. So the direction of time, which is arrow of time, is determined by entropy. If energy has an opportunity to spread out, it will. If molecules can mix, they will. If temperature difference can equalize, they do. That's why entropy is called the arrow of time. Time flows in the direction in which entropy increases. So that's all for entropy. And see you in next videos. Do not forget to like, subscribe, and support me on Patreon. With love, Şevval.